Hello class, welcome to lecture 18. So today we're talking about confidence intervals again, but this time we're talking about examples instead of all the theory. Today is my last day at a hotel, so after this I'm back to my usual setup. I'm also trying out a new hairstyle, so I'm wearing a hairband today because my hair is so long. Oh wait, I took it out, never mind. This is just, now it's stuck up from being in my hair all day. Okay, anyway, back to the math. So we're going to use what we did last time, but now we're just going to do actual problems to see how that theory should be used. So remember that the idea was that we take a sample and we can't really say for sure how close our sample is to the actual proportion, but instead we make these confidence intervals and say how confident we are that the interval contains the real proportion. That's the idea. Okay, so here's this big old example that I pre-wrote because it's so long I didn't want to write it on screen. Okay, so in the Parent Teen Cell Phone Survey conducted by Princeton Survey Research Associates, very fancy, international, 800 randomly sampled 16 to 17-year-olds in the US were asked whether they have used their cell phone to text while driving. So before continuing, first of all, I don't know why this is highlighted in a box, but the first thing you should notice is, oh, it made everything blue on accident, okay. That the sample size is gonna be 800 because 800 people were randomly sampled about this question. So they were asked whether they've ever used their cell phone to text while driving. And then 272 of them said yes. That's gonna tell us our proportion. And then lastly, what they want us to do is obtain a 95% confidence interval. And we'll go through that. Okay, for the proportion of 16 to 17-year-olds who text while driving. So the idea is we are going to create an interval around our sample proportion. That's all we're really doing. Okay, but I'm going to break it down in steps. So step one, let's just say what we're trying to do. So we are trying to find the interval, so like a range of numbers between blank and blank, around, the fancy terminology is that this is called the point estimate, but it's really little p hat, and it's really your sample proportion. So in this situation, 272 people said that they have done this out of 800, so that is our proportion that answered that they do this. Oh, sorry, my iPad got disconnected for some reason. Let me try to bring it back. Okay, we're back. Sorry, I'm having lots of internet trouble today. It's very delayed. Okay, I'm just gonna pause and come back. Okay, so as I was saying, we're trying to find the interval around our sample proportion, but people always call this a point estimate. So that's another name for this stuff. We named it that last time. So we're trying to find the interval around this number, which I'll round to 0.34, where we can be 95% confident that the true proportion of people that do this thing, which is the true proportion of 16 to 17-year-olds who text while driving, is in there. So that's the idea. We want to find the interval around our sample where we can be 95% confidence that the true proportion is in there. And 95% confidence has a real meaning. It's not just like, yeah, I'm really confident, and I'm just sort of saying that with my gut or something. No, it has a mathematical thing, so that 95 will come in later. Okay, so that's what we're really trying to do, but really your first step is just calculating the point estimate, 0.34. Okay, so now we need to get the z-score corresponding to an area of 0.95 under the bell curve in the middle. That's what we need next. And so this is not going to ever change. As long as you're doing a 95% confidence interval, then this z-score that we're about to get will be the same on all those other problems too. So then, because stats people like to have confusing things, they name everything. So they call this z-score the critical value. So you'll hear this term too. So you can go look it up, but it's 1.96. And the idea is that, so what does that 1.96 refer to? It refers to the fact that if you have your z-score distribution where 0 is in the middle and the standard deviation is 1, then if you go out to 1.96 on both sides, so you go out to 1.96 and negative 1.96 standard deviations to the right and to the left, then the amount of area under the bell curve is 95% of the area, where the total area is 1, so that's why it's 0.95 out of 1. Okay, but the important fact is that we need this 1.96. So if it was a 90% confidence level, then it wouldn't be 1.96, it would be something else, corresponding to 98% area. So then we have to introduce even more terminology. So people also use this terminology called alpha. So you'll see this if you ever Google confidence interval or something. So people also associate critical values with something called alpha. So it's the Greek letter alpha. And here alpha is 0.05. So why do they name this? I don't know, because it's just this. It's just the opposite of this number. So how are these two numbers related? You might be able to see it right now. They add up to 1. So the alpha level, the alpha is just the rest of the area, how much area there is total on the outside of these two z-scores. So the blue area is 0.05 of the area, which also means, by the way, that this side is 0.025 and this side is another 0.025 because it's symmetrical. So that's always what alpha is. Why does it need its own name? I don't know. So it's really just the amount of outside area, which is 1 minus 0.95, which is 0.05 in this problem. So the more stats you see in this class, and the more I teach it, the more I realize that like people just say the same things over and over and over with different names. And then they like think they're really cool, I guess, if they can do that. I don't know why they do that. Okay, so in any case, all we need here is this z-score. That's all we really need from this step. So then the idea is that the interval that we're trying to build, it extends that many standard deviations, so 1.96 times the standard deviation of the distribution. Our interval extends that far away from our point estimate. So we don't know the standard deviation yet, so that's going to be the next step. So that's what we need next. And we have a formula for it, but it's a little bit trickier than just using that formula. So what is this standard deviation of the normal distribution of the sampling distribution of the sample means? That's the fanciest possible way to say all this. Well, it was this number that you get by doing the square root of the proportion times 1 minus the proportion over n. So we calculated this in a lot of examples before when we were doing the reverse problem, which is we were trying to build the distribution. And this time we don't know the proportion. So we don't know P, that's not given to us like it was in those other problems. And then we used it to get the standard deviation. We don't know this, that's the whole point of confidence intervals. We don't know the true proportion, we're trying to estimate the true proportion with our sample. So how the heck am I supposed to calculate the standard deviation if I don't have this number? Well, this is stats, so we just do the best we can do. It's not perfect. The best we can do is use something that we do have, which is a sample proportion instead. So that's what we're going to do. So if I already knew the true proportion, well, then there would be no point in making the confidence interval in the first place. So I wouldn't even be doing this problem. But because I don't know the true proportion, I'm trying to estimate it by creating an interval that hopefully has it inside of it. I need to use the only thing I can use, which is this instead. Okay, so this is not the actual standard deviation. This is our best guess for the standard deviation. Okay, so we use 0.34 here, 1 minus 0.34, and then our sample size, remember, was 800 people. 800 16 to 17-year-old teens were asked this question, so that's our sample size. Okay, so then use a calculator for this, and you get 0.0167 roughly. And so again, this tells us how wide the confidence interval is. So we just need to multiply it by that critical value that we had. So the z-score is the amount of standard deviations out that you go, and now we know the size of the standard deviation. So we multiply it together, and once again, the stats people, they just have to introduce extra words for no reason. So this number, which is really just how wide the confidence interval is, it also has its own fancy name. Okay, so just do this multiplication on a calculator and you get that. The fancy name is, it's called the margin of error. Because the idea is, this is how far out from your estimate you think that the real answer would be inside of. So I guess you would say this is how much error you're allowing your estimate to have. So I guess that's why they call it the margin of error. But anyway, it's really just how wide your confidence interval is from the middle, from the point estimate, from the sample proportion that we started with. So what that means is I just have to now take our sample proportion, our point estimate. This is the last calculation-y step. And then I'm just going to add that much. I'm going to add my margin of error. And that's going to get me the right side of the confidence interval. So if I do that, I get point. Let's see, what is this? This should be 0.3728. So this is the right side of the confidence interval. This is how far to the right we think that the true proportion might be. This is as far as to the right we think it could be in. And then we also go to the left. So now we take the point estimate, oops, 0.34, and we subtract that same amount. So that'll get us the left side of the confidence interval. So 0.34 minus 0.0328, that'll get us down to 0.3072. So this is really the end of the mathy portions. We just need these two numbers, and now we have to answer in context. So our confidence interval really is from the smaller number to the bigger number. So it's from here to there. Okay, so now we just say the answer in context. So then these confidence interval problems, we always want to answer in a very particular way. So we got to say it just like this. We are 95% confident. We have to say that amount because we used a critical value corresponding to 0.95 area. So we are 95% confident that the actual proportion, which now we have to say the context of the problem, the proportion of 16 to 17-year-olds that text and drive is between, and then we say the confidence interval, 0.3072 and 0.3728. And that's the end of it. So all the confidence interval problems are going to go just like this, just these 5 steps, but they go much faster once you're used to it. So again, the idea is like, here's like a number line from, here's 0.3072 and 0.3728, and it's surrounding symmetrically my point estimate, 0.34, and I'm saying that I don't know where the true proportion is. I don't know what this is, but I'm 90% confident that it's somewhere in here, where 95% confident is a technical term to mean all the stuff that we did. Okay, so that's the end of this problem. And so what can change is if you go back through it, and so on the lecture problems, when you do them, you have to notice these things. So what can change? Well, the sample proportion that you start with, that can certainly change. You'll use some other number. The confidence level can change. It's always going to be 95, 90, or 99. It's always going to be one of these 3. For some reason, that's what people like to use. And so then I will put on the lecture problems the z-scores, the critical values for these other ones. So this critical value is only for 95% confidence level. If you use 90% or 99%, you're going to use a different critical value, a different z-score. But then, so then your alpha will be a little bit different, but the alpha doesn't really come into play. But what will change is, instead of using your 1.96 critical value that I used, if your confidence level is different, this will be different. So it's really just going to be one of 3 numbers. It could be the one for 90, it could be the one for 95, which is this one, or it could be the one for 99. And then your standard deviation is going to change because you're going to use whatever sample proportion you have in your specific problem. It could be something else. But then you're still going to calculate this number using, and then your sample size might not be 800, it could be something else. But then after that, you're still going to multiply your critical value. So it could be, again, 1.96 or one of the other 2 numbers times this thing you just calculated. That's going to give you your margin of error. And then you're going to take your point estimate that you started with, which could be different than this, and you're going to add that to this number that we just got, the margin of error.